Hello, and welcome to this talk. I will be talking about optimal differentially private learning of thresholds and quasi-concave optimization, which is a joint work with Edith Cohen, Jelani Nelson, Tamás Sarlós, and Uri Stammer. Here is an outline of this talk. I will start by introducing problems, motivating them, and surveying prior works. And then I will summarize our new results. Next, I will give you some high-level proof ideas of our improvements. And then I will conclude with some discussion. So most of this talk will be about privately learning thresholds, and we'll have only one slide covering the quasi-concave optimization result. So let's go into part one, background. So let me start by defining a problem not exactly learning thresholds, but very closely related, which is called private approximate median. So here you are given as input an array of integers, x1 through xn. Each of them is assumed to have value 1 through n. And you are tasked to output a integer y from the same domain, where y is supposed to be an approximate median of x. So what do we mean exactly by approximate? Here, we will choose to mirror the error of your algorithm by rank. So namely, we desire your output y to be really in the middle of your data, which means there has to be at least n over 3 elements less than y and n over 3 elements larger than y. So it's also important to note that y is not necessarily in this range in xi, because otherwise it's impossible to design a private algorithm, which I will introduce now. So we have this privacy requirement, which informally says that changing one input of the integer arrays does not change the output distribution too much. More formally, we say that a randomized algorithm A is epsilon comma delta differentially private if for every two adjacent data sets x and x prime that differ by only one entry, and for any possible subset of outcomes E, the probability that A of x outputs a solution in the set E is upper bounded by E to epsilon times the same probability concerning x prime plus an additive failure probability of delta. So let me also remark that we mirror the error by rank. The mirroring error by rank turns out to be a more robust requirement than mirroring the error by distance. And moreover, when your data is concentrated around the median, then the approximate median by rank is close to the true mean just by distance. And here, the big question we want to ask is, fixing the parameters m, epsilon, and delta, what is the smallest n so that the problem is possible to solve? So this question does not make much sense in the non-private world, because as soon as you get one data, you can start defining what median is and finding out median rather trivially. So that's private median. And now I will introduce another problem, also closely related to learning thresholds, which is called private interior point problem. It's basically the same as private median, but with the requirement being seemingly relaxed. So now you only want to find out the integer y, which is between the smallest and largest elements of the input array. Right, and again, the question we would like to ask is, given the domain size capital M and privacy budget epsilon delta, what is the smallest n so that the problem is possible to solve? And again, without privacy, this problem is trivial. As soon as you get one data, you can just solve the problem. Okay, so that's the two problems not really about thresholds. And now comes our main task of study, which is private pack learning of thresholds. So we use the standard pack learning setup, which said that there is an unknown distribution D supported on M with plus and or minus labels. So M is the query or input domain, and plus minus is usually called labels. And we have an unknown hypothesis H, which is consistent with the data, which means for every sample x comma b from the distribution D, H of x agrees with B. And we assume the hypothesis is H in the form that there is a hidden parameter Y, and H of X is just the indicator that X is greater than or equal to Y. And right, we use, in the standard pack learning setup, we have a collection of n samples drawn independently from the distribution, and you would like to find out with good probability a hypothesis H hat, such that H hat has a low generalization error, let's say as low as 0.01. And we have the privacy requirement, which says that arbitrarily changing one input does not change the output distribution too much. So we just use the standard epsilon comma delta dp definition. And here you can see, since we assume the hypothesis is a threshold function, so this is the problem of learning thresholds. And we are asking, again, the same question, given capital M, epsilon, and delta. And also, let's say we fix the confidence parameter to be 99% and accuracy to be 0.01. What is the smallest number n so that the problem is possible to solve? Here, without privacy, this problem is not that trivial, but still, the standard VC theory tells you that without privacy, you can solve this problem just with a constant number of samples. And it works for any distribution D. At least for any realizable distribution, which is the only case we will consider today. And now let you tell me some connections. Why did I introduce two seemingly unrelated problems to you? And actually, it turns out all the three problems we have just discussed are equivalent in terms of sample complexity in the privacy-preserving data analysis context. So we use the symbol A array to B, means an algorithm for A implies an algorithm for B with similar sample complexity, or yeah. So let's put at the center the interior point problem, and we have the approximate median problem and the learning threshold problem. I guess it's rather trivial to say that if you can solve approximate median, then the approximate median you find is just going to be a very good solution for the interior point problem. And turns out the reverse direction is also true. If you can solve interior point, you can solve approximate median with asymptotically the same sample complexity. So actually, the reduction is quite simple. What you will do is you just remove the largest and smallest over 3 elements from your data set, and you solve interior point problem on the remaining data. It gives you something which would be a very good approximate median for the original data set. And turns out we can build the same connections between interior point and learning thresholds. So just for one direction, let's see how interior point, an algorithm for interior point implies an algorithm for learning threshold. So here, what you can do is, given a collection of samples for the learning threshold task, you can take out the n border samples, by which I mean you take out some largest negative samples and some smallest positive samples, which in this case, in the picture, let's say it's all the 8 samples enclosed by the bracket. And then you can solve interior point on these border samples using the assumed IPP algorithm. It gives you X interior point, and then you just output the hypothesis defined by this interior point as your output hypothesis H hat. So why does this reduction make sense? Well, at first, it's not hard to see the, if you require a rigorous proof, then you need to do some work. But intuitively, it's not hard to say that this algorithm has generalization error as low as 0.01. So this number comes from the ratio between 100 n and n. So this follows because your algorithm can only classify the samples in the bracket region. So for samples below or above this border region, your algorithm will just perfectly classify the inputs. And in terms of privacy, it's not hard to convince yourself that changing one input sample can only change a constant number of border samples. So if you assume your IPP algorithm is private, the final learning algorithm for thresholds would be private as well. So that's one connection. And turns out you can build the other direction, which said that learning thresholds gives you an algorithm for interior point with similar sample complexity. And there are two more problems, which I will not discuss or define today. So it's just it suffices to know that they are all basic and fundamental tasks in the privacy preserving data analysis context, and both of them are closely connected to the interior point problem. So for today's talk, we'll just try to understand the sample complexity of this IPP problem. So what can we say about the interior point problem? Let us review the problem again. The input and integers, each one being finite, and output integer y, which is sandwiched between the small and largest elements of x. And you have the privacy requirement. And we ask the question, how large should n be so that the problem is possible to solve? So as a warm-up, it's not hard to see that with only two inputs, you cannot solve the problem. So here is a demonstration by figure, which I don't have time to explain in detail. But it turns out the problem is actually impossible to solve when m becomes arbitrarily large. So in particular, in this 2015 paper by Bohm, Lissam, Stammer, and Wadang, they showed that n has to be at least omega of log star m, where log star m means the minimum quantity t such that you have to take logarithm on tm for t times so that the resulting quantity becomes less than 1. So in particular, this means the problem is impossible to solve when you only assume the input array is taken from reals, and if you assume it can be arbitrary or worst case. Okay, so since this, there has been a long line of works concerning this problem, aiming to get better upper bounds or lower bounds, because this is a very basic problem in privacy data analysis. And once you have a definition of privacy, this has to be one of the first few problems you want to understand. So in terms of upper bound, the very first paper, very early paper by Bemo, Kasvisa, Nathan, and Nisa showed that if you just run the exponential mechanism, it gives you a private learning threshold algorithm with sample complexity O log n. So the algorithm works even in the pure DP setting, and also actually in the DP setting. In the pure DP setting, there is also known as omega of log m lower bound. And this result was improved by Bemo, Lissam, and Stammer in 2013, bringing the sample complexity down to 8 to the order of log star m. And it was further improved to 2 to log star m. Compared with this log m upper bound, this is, it's even more than exponential improvement. And in 2020, Kaplan, Leggett, Masson, Noll, and Stammer further improved the upper bound to log star m to 1.5, which is again an exponential improvement, and which is also polynomially close to the lower bound. And for the lower bound side, since this 2015 lower bound of omega log star m by Bohm, Lissam, Stammer, and Wadang, there has not been a quantitative improvement. But qualitatively, I should say that the BNSV lower bound only holds for the setting of proper learning, which means the algorithm has to output a threshold. For the more general setting of improper learning, a recent work by Arnaud et al. Also showed the same lower bound of omega log star m. So in summary, before this work, our understanding of the sample complexity is somewhere between log star m and log star m to 1.5. And now let me introduce our work, where we show a new upper bound of O tilde of log star m. So up to lower order terms, we have basically closed the gap between the previous upper and lower bounds. If you want to be precise about the asymptotic, or if you care what's hidden in the O tilde notation, well, let me spell out the sample complexity precisely, is log star m over epsilon times log squared of log star m divided by epsilon delta. To compare, the best known lower bound is omega 1 over epsilon times log star m times log 1 over delta, which is available in Mark Bone's PhD thesis. So here we are off by a log 1 over delta factor and log of log star m factors. But that's, I mean, if you are willing to accept lower order terms, we have basically determined the sample complexity of this basic privacy data analysis problem. And here is one more slide for the related problem of quasi-concave optimization, which I'll just be very brief and not focus on it today. So here is a definition for quasi-concave functions. Let's imagine you have a function f, which takes as input a data set D and a candidate solution, let's call it B, and then it outputs an integer quantity, which measures how good their solution is with respect to your data set. And the optimization task is called quasi-concave if for every three, increasing solutions A, B, and C, the quality of B is no better than the best of A and C. So this is what we mean by quasi-concave. And the task of private quasi-concave optimization asks you to do the following. So you are given as a public information a sensitivity 1 function f and a data set D. You would like to find a solution y which approximately maximizing f of x, f of D and y. So, I mean, also you want to be subject to the epsilon comma delta dp constraint, and you want to minimize the suboptimality gap, also known as additive error. This is to say, if y star is the best solution with respect to your data, you would like to find out a solution y such that f of dy is as close to f of dy star as possible. So 2 remarks on this problem. First, you can see this, I mean, it's not hard to see this problem generalizes approximate median because you can define your function f to quantify how middle your solution y is with respect to your input. It is also useful in many other tasks. Most notably, is useful in learning half spaces in higher dimensional space. And before our work, the additive error for this problem was known to be somewhere between lower bound log star m and upper bound 220 of log star m. And I mean, since we have at least a series of algorithmic improvements on the interior point problem and quasi-concave optimization being a closely related problem, it's conceivable that the similar algorithmic improvement can be made here and get us a polynomial in log star upper bound. But unfortunately, and somewhat surprisingly, we show it's not the case by giving both an improved upper and lower bounds. So in particular, up to lower order terms, we can show that the achievable error for this problem is of order 2 to log star m. So this is, I mean, this means that the most general form of private quasi-concave optimization is a strictly harder problem than private interior points. And now I have summarized all the new results we have to offer. And now let me move on to give you some high-level ideas of the proofs. So in particular, we will focus on the result of learning thresholds. So actually, we are achieve our improvement by introducing and analyzing algorithm framework that we call reorder, slice, and compute. To start, let us give a very brief overview of the previous upper bound of log star m to 1.5. So here we are trying to solve the private interior point problem, which, if you still remember, you are given as input an array of integers, and you would like to find out an output that is sandwiched in your data. So you have input x, and you set a parameter t, which is of order 1 over epsilon. Here, the epsilon is a private C parameter. And you do the following. So you iterate for log star m rounds. In each round, you sort your current input, current data X, and then you take out the smallest and largest T elements out of your data. And for the remaining part of your data, you apply an embedding function, which shrinks the size of the domain from X to log of X. And yeah, that's it. So this embedding function is a highly sophisticated procedure designed in the paper by Kaplan et al. But for the purpose of this talk, we don't need to understand what exactly does it do. But so all important here is that it shrinks the size of a domain from X to logarithm of X. So since each time you can shrink the size of the domain by taking a logarithm, it's imaginable that after log star m rounds of iteration, you are left with a domain of constant size. And for simplicity, let's just assume that the domain is of size 1 in this in this presentation. Then you can imagine that after this series of reductions, you are left with a domain of size 1. Then you can trivially set up a solution, which is just 1. And then we assume this solution is a solution for the reduced instance, and we want to apply a series of upgrades or lifting to get a solution for the original instance. So to do that, we iterate. So for I from log star m to 1, for in each round, we update our current solution by using the slice we have taken during the ith iteration of the previous for procedure. So again, this update is a sophisticated procedure designed in the paper. But for the purpose of this talk, you need to know that update is an epsilon private procedure with respect to this slice, and it takes a solution for the recursive instance and gives you back a solution in the larger domain. So it's imaginable that after log star m rounds of iteration, you get a solution for the original domain of size L, which you just return it. So here we have two mysterious embed and update procedures, but for the purpose of this talk, it's not very important what do they do exactly, but I just want to highlight the algorithm framework in the framework hidden in this whole algorithm. So this is the procedure we call reorder slice compute. So to explain, let's say that in each you are doing an iteration. We are in each iteration. You first sort your current input, which corresponds to the reorder step, and then you will take out the smallest and the largest elements according to the current ordering, which is the process we call slice. And after this actively reorder slice and recursion, you get a bunch of slices, and you use these bunches of these slices to do some computation, where you can see in each round, you use one slice to apply one private computation. So that's what we call the reorder slice compute framework. Okay, so let me briefly explain how you got the log star m 1.5 upper bound through this algorithm. So as you can see, there are log star m rounds of iterations in total. And for this whole recursion to go through, you have to have 2t times log star m many samples, which is of order 1 over epsilon times log star m. And since you have applied log star m rounds of private computation, where each round is epsilon private with respect to the slice in that round, you can apply roughly the advanced computation theorem to say that the final privacy bound of your algorithm is epsilon prime, which is epsilon times square root of log star m. Since you desire your final algorithm to be a private one, so let's say you desire the final algorithm to be 0.1 private, then it means you have to set epsilon to be 1 over square root of log star m, which brings the total number of samples to log star m to 1.5. So that's the previous algorithm. And we ask how to improve. Well, very intuitively, you can see each item only participates in one computation. and you shouldn't really pay the composition loss. So that's our intuition or idea for the improvement. But however, this idea can be very tricky to implement because the slice is highly data dependent. So see for example, the following two pairs of data sets. In one data set, we have x1 through x9, and let's suppose they are just sorted. And let's now consider an adjacent data set where I replace x2 with a very large element called x prime 2. And then I do slice on the two data sets with slice size set to 3. I get two lists of slices. And if you compare these slices one by one, you can see all of the pairs are different, which means that in general, you really should pay the composition loss. And our idea for improvement is that if you just slightly randomize the slice size, it suffices to offer you a improvement. So here presents our framework, which just do this reorder slice, actively do reorder and slice, but each time with the slice size slightly randomized, and then you can do arbitrary private computation on each slice. What we can show is that compared with the naive analysis, which give you something like square root number of slices times epsilon private bound, we can get a private bound which is independent of the number of slices. So let me wrap up. In this work, we present a new O tilde of log star m upper bound for private interior point problem, which is obtained by slightly modifying the previous algorithm and then analyzed under our new framework of privacy data analysis. It implies improved bounds for post-O problems. And this algorithm improvement is only possible through this reorder slice and compute framework, which extends and generalizes several previous ad hoc analyses. It looks quite general and would allow to see more applications. And it's also worthwhile to compare with the privacy amplification by subsampling framework. Lastly, we demonstrated an exponential separation for the related problem of quasi-concave optimization, which means that if you want to make progress on the more general problem of learning high-dimensional half spaces, we might need new techniques. And that concludes my talk, and thank you for your attention.